Now, before we move on, I just want to revisit the definition of the manifold a little bit. So let me just go back. Right. All right. So in particular, I want to revisit point 3 because I want to define not just a manifold, but a manifold with a boundary. So differential manifold with BDY. I will use the short form for boundary, BDY. So manifold with a boundary is slightly different from this normal manifold. Okay. In manifold with a boundary, what we'll try to do is, instead of mapping each open set, the first two will remain unchanged. So it is, of course, has to be a Hausdorff space, and it has to be covered by a countable collection of open sets, UI. Now, for a manifold with a boundary, each open set U sub I is going to be homeomorphic to O sub I, where O sub I are open sets of the half space Hn instead of Rn. Okay, Hn. Okay, so for manifold with the boundary, every open set or every coordinate patch is homeomorphic to an open set in the half space Hn. If you're not familiar with the concept of half space, let me define it. A half space Hn can be thought of as the Cartesian product of Rn minus 1, n minus 1 dimensional Euclidean space with the half line R1 greater than or equal to 0. So this is n dimensional because n minus 1 Rn minus 1 and times the, let me just rewrite this, it's a bit ugly, greater than or equal to 0. Alright, so I'll give some example. For example, consider R2. And now if I restrict myself to the upper half, that is only y positive, and y, if I restrict myself to y greater than or equal to 0, the upper half plane, as you will say, or if you want to be more accurate, the closed upper half plane, which means it includes the x-axis. This is an example of a half space because this will be R2 is product of R1 times R1, but the half space, which is the shaded region, will be product of x direction is there. So R1 times y coordinate is only allowed to have positive values, so this will be R1 positive greater than or equal to 0. So this is actually called the closed half plane because it includes the axis. If you have manifold with a boundary, for example, you can have a hemisphere, right? The hemisphere has some boundary. This cap-like surface, it has some boundary. Now, open sets of this guy, this is, let's say, an open set, is mapped to an open set of the closed half space, okay? N-dimensional half space, which is given by this. All right, Hn, this is given by Rn minus 1 times R1 positive semi-definite. Okay. Just like H2 can be, so this is H2, the shaded region. H2 is a subspace of R2, subset of R2. We can use the induced topology to find out open sets of H2. Okay. I hope people have not forgotten the concept of induced topology or relative topology. If you have some topological space which has some open sets, you can always hook up topology for the subspace of a subspace And that topology is called, which is inherited from the larger space, is called the induced topology. So because the half space Hn is a subset of Rn, topology is induced in Hn. Automatically you get to know the open set of Hn if you know the open set of R, which will use to be the standard topology. So I wanted to mention this because in this course we'll definitely look at manifolds with boundary. The manifold with boundary, locally they will look like open sets will look like open set of Hn instead of Rn. And then the smoothness criteria is not going to be changed, so only this third point has to be amended for manifolds with a boundary. All right, let me go back. So we covered everything, like all the examples. We've covered what charts and atlases are, what is an equivalent atlas or comparable atlas, and we know what is the maximal atlas. And let me come to this topic of smooth maps between manifolds. So we are discussing a smooth map from one manifold, say MM. So it's a little m dimensional manifold, and map from MM to NN. Okay, so big N is the manifold, and little n is the dimensionality of that. Okay, so this is the function I'm talking about. All right. So in the next next slide, I have a picture. Right. So M is this, and F is a map. So it takes a point P on M and lands it to a point F of P on M. Okay. All right. So this is just a map. It's not yet a smooth map. I'm yet to set up the conditions of a smooth map. But let's start with this minimal. We have some map F which takes you from M to N. All right. Here, let me come back to this diagram. So we have M, we have N, and then there is a function or a map which takes you from P to F of P, a point F of P. Now, because M is a manifold, there are open set, and P might be contained in one of those open sets. Let me call this U. And also the image point F of P will be contained in some coordinate patch of N. Let me call that U. Sorry. And this is B. That's it. Okay. These 2 points also lie in these respective coordinate patches. Now, every coordinate patch comes with the homeomorphism phi. So, under this homeomorphism phi, this pre-image point P will be mapped to the coordinates of P, which is X, right? At the bottom here you can see. And similarly, this F of P, the image point, lies inside this coordinate patch V, which comes with its own homeomorphism psi. That means, using psi, if I feed F of P to the argument of psi, it's going to give me the coordinates of this image point F of P, which is 1. So psi, and the argument is F of P. Okay. So let me go back to the previous slide. As I was saying, that P is contained in this coordinate value phi. That means phi of P gives me the coordinates of X, and I can invert this to write P as phi inverse of X. Similarly, the image point F of P in N is contained in another coordinate chart, a different coordinate chart in N. And psi, if you feed the image point, that gives me the coordinates Y of the image point. So psi of F of P. Now, instead of P, in this P, I can always substitute this here. And then I get psi of F of phi inverse of X. So Y equals psi of F of P, and then P I substitute to be phi inverse of X. So I get this composite map, psi of F of phi inverse of X. So this gives me the coordinates Y as a function of the coordinate X. The coordinates of the image point and coordinates of the pre-image point, they get related. Okay. Now, in particular, a better way to phrase this is that the coordinates of the image point become a function f tilde of the coordinates of the pre-image point. Okay. And remember, the pre-image point coordinates are Rm. It's a M tuple, while the image point coordinates are lie in Rn. Right. So it's an N tuple. So this f tilde is this composite map psi of f of phi inverse. This composite map, f tilde, is a map from m real variables to n real variables. So this is something we are already familiar with. This is just multivariable calculus, which we have learned in undergrad. So it's a function which takes from as input m real variables and spits out n real variables. So this we know, and we say that the original map between the manifold F is smooth if this F tilde is smooth. So now F tilde is normal multivariable real calculus, so we can define smooth functions. That is, the y's are C infinity functions of the x's. Okay, all order derivative of the components of y. Remember, the components of y are denoted by y alpha, not mu, because mu takes values from 1 to n, but alpha takes values from 1 to n. Okay, they're different. So the y alphas are smooth functions of the x's. If this happens, then we say the map F is smooth. Now you might be worried that this map F tilde actually needs knowledge of psi and phi inverse. So maybe if I go to a different chart, these criteria of smoothness might change because I will be using some other chart, like let's say psi prime and phi prime, and maybe it is going to be smooth in this psi and phi coordinate, but not in the psi prime and phi prime coordinates. Who knows? But actually, that is not the case. This definition of smoothness is actually chart independent, just because of the fact that overlapping charts in a manifold are stitched smoothly. The coordinates are smooth functions of each other. So I'll refer to the notes for the argument for the few lines of algebra which demonstrate the chart independence. Please look at the notes. Just a few lines, 1 or 2 lines. All right. So this is the diagram. And I can give him one example. Maybe it's a good example to give. Now, this is the embedding map. The unit circle can be embedded as a curve inside R2, right? One can think of the unit circle, S1, as a one-dimensional curve inside R2. Then R2 points in R2 are given by coordinates x, y. Right? X, y. But on the circle, it's a one-dimensional manifold. So let's say the coordinates on the circle are given by theta, this coordinate. And then this embedding map can be given as x equals cos theta and y equals sin theta. So this realizes the unit circle as a one-dimensional curve embedded inside R2. Okay, so this is sometimes called the embedding map, and this is a smooth map. Why? Because x and y, these coordinates so n is going to be R2, and m is going to be S1. Okay, so this map is given by these equations. So this is actually the F tilde map because I'm writing down the map between the coordinates. So these are smooth functions. Cos theta is a smooth function. It's infinitely differentiable. And sin theta is also a smooth function. Infinitely differentiable, right? In the interval 0 to twice of pi. So this embedding map is a smooth map, so which maps S1 into a surface in R2. Okay? So this is one example. All right, let me come to diffeomorphisms, which is a very special category of smooth maps. So smooth map F from Mn to Nn. So now you should notice that the dimensionality are the same. Diffeomorphisms are only defined between manifolds of identical dimensions. Okay, so a diffeomorphism F from Mn to Nn is defined to be a smooth map for which the inverse exists. Condition 1, inverse exists, and secondly, the inverse is also smooth. Okay, both F and F inverse are smooth. Okay. If this is so, then M and N are said to be diffeomorphic to each other, and the fact that they are diffeomorphic to each other is denoted by the symbol of this equivalence. Okay, M equivalent to N. In the sense of differential geometry, if two manifolds are diffeomorphic to each other, we don't treat them as separate manifolds. We think them think of them as the same manifold. Okay, one can be smoothly deformed to the other. Contrast this idea of a diffeomorphism with homeomorphism, which we learned in the previous lecture, in which if one object or space, topological space, can be continuously deformed from one to the other. So continuous deformation versus smooth deformation. Continuous deformation in homeomorphism versus smooth deformation in a diffeomorphism. They are distinct. So continuous means C0 in the language, sorry, in the notation of math, C0, and smooth is C infinity, infinitely differentiable. One example would be, consider the V-shaped segment and the straight line. Okay. Now these two are homeomorphic to each other because I can deform this, pull this down without cutting and gluing and turn it into the real line. But these two are not homeomorphic because the derivative at this point is indeterminate. On the other hand, for the derivative at the image point is not. So this V-shaped segment cannot be deformed. Smoothly deformed into the real line. It can be continuously deformed, but not smoothly deformed. Okay, so these two are not diffeomorphic, but they are definitely homeomorphic. All right. So the punchline is that if two manifolds are diffeomorphic, we don't really treat them as different manifolds. And let me give you an example. Again, my favorite example is always going to be involving the unit circle S1. Consider the S1 and the ellipse. The fact that these are diffeomorphic, perhaps you can just just look at the corresponding graphs and say that okay, it seems like they're going to be smoothly deformed into one another. But more explicitly, both can be realized as curves inside R2, right? This is the ellipse, and this is the equation for the this is the curve which represents the circle. And it's very obvious that if I define this change of coordinates, big X to be little x over little a, and big Y to be little y over little b, these two functions, big X as a function of little x is a C infinity function, and same because it's a linear function. Of course, all higher order derivatives are 0. First order derivative is just 1 over a. Same for the case of y, and you can also invert them. That will also be C infinity. So the circle and ellipse are diffeomorphic to each other. Now let me conclude by mentioning a very special set of diffeomorphisms. All possible diffeomorphisms of a manifold to itself. Okay, all possible diffeomorphisms of a manifold to itself. So f of m from m to m. So these form a group, and this form a group because of the conditions of a diffeomorphism. The inverse exists. The inverse is a smooth map, and of course the identity element is of course there. This means identity transformation. And also the fact that composition of maps is associative. This is something which you probably have already learned in high school, that f of g, of h is equal to f of g of h. So maps, such composition of maps is associative, so it satisfies all the properties of a group. So all possible diffeomorphism of a manifold to itself form a group, which is denoted by the symbol diff of m. Okay, diffeomorphisms of m. So this is very important in physics, especially in GR, because this gives you the set of active transformations. So let me just draw this manifold M, and then under diffeomorphism, some point is moved to some other point. So P is moved to some other point on M, which is called f of P. Okay. So if you recall from your undergrad, there are two ways of thinking about symmetry. For example, if you consider rotation symmetry, one is that you can keep the point same and rotate the coordinate axis, which is the passive transformation, and the other is the active transformation, in which the coordinate system remains fixed, but you rotate the point. Okay, you move the point to a rotated location. So this active way of thinking about general coordinate transformations is given by this diff of m. All right. So let me just go back to the definition of this transition function. because I wanted to emphasize this point of passive transformations. Yeah, so this transition maps between two overlapping charts. So this point P will have two set of coordinates coming from two charts. And remember, in the physics language, two coordinate charts are just two coordinate systems. So this transition maps relate coordinates of two different coordinate systems. All right, two different coordinate systems. So this is the situation where we have the same point, but we have two coordinate systems. One is the original and the rotated coordinate system. So this is like a passive transformation in general relativity. Right. So we will end the lecture here. Our agenda is complete. So let me summarize. So we first introduced the idea of a differentiable or smooth manifold. We introduced the idea of associated ideas with the coordinate charts, transition functions. We introduced the idea of atlas, compatible atlases, and most importantly, the maximal atlas, which is what we're going to assume, and we're going to pretend that the maximal atlas is unique as well. Now, the maximal atlas endows the differentiable manifold with something called a differential structure. We then introduce the notion of a smooth map between manifolds, and in particular, a very special category of smooth maps which are invertible, and the inverse is smooth, which are called diffeomorphisms. And finally, we discuss this group of diffeomorphisms of a manifold to itself. They form a group, and this is how you study active transformation way of looking at general coordinate transformation in general relativity. All right. In the next lecture, we'll set up calculus on smooth manifolds, where we will learn elements of tensor calculus and manifolds. So thank you very much for your attention, and see you next time.